Oops. The time that Tim Peake went into space, and before then I got quite interested in having a go at the ISS tracking, but mechanics were always difficult for me, and I played around with this, more or less as I'm going to show you, but I didn't get it done in time, so decided to forget about it. Then when I heard he was going back into space again, although we don't know yet, do we, when he's going? No, he is going, I thought. That's the main thing. I thought I'll have another look at this. So this time I asked Rob M0DTS for his help on machining things, because the difficult thing I was finding was joining the two hard disk contraption together. So Rob has kindly machined that middle bit, which is, has done the trick. It's a very complicated double tapered hole, to be technical. So before I looked at this, I looked around at the options, which seem to be very expensive. G5500 works very well, but quite expensive. The Spideraz, even more so. And there are several homebrew systems with stepper motors and pots. Well, I'm sure we've all seen the G4KLB system, which works very well. I looked at that and thought, a bit complicated that. There's the VK5 DJ beam controller, I think it is. Pots and gearboxes and sensors, wiring for that at the back, I think. What put me off the most was mains. I'm working with logic circuits mostly. I'm used to putting my finger down the end of the probe to see if it's open circuit or not. So I wouldn't last 5 minutes with mains, so I decided to avoid that. So I thought, is there a simpler way of doing it? And I'd used these domestic satellite positioner motors for years. I thought, wonder if there's a way of doing it more simply. The good things about these are that you just tell them the angle to go to and they just go to it. There's no feedback at all. It's very, very simple. So I looked at various models, and this TM2600M3 seemed to be well thought of. So two of those, you take the arm off that usually has the dish on it, leaving you with that stubby rotor, and you connect them together. It sounds simple, but it's quite simple when you have the proper machine part. The other good thing about these rotators is that they use the DiSEqC protocol. You just you pulse things on the 18-volt supply line at 22 kilohertz, and you can send commands to them. So you just say, go to 20 degrees, and they just go there. And it's that simple. So the controller is it's one I've made up as a test. It's very much simpler than the previous one that we saw. It's just two channels of DiSEqC control, which I'll explain later, and an Arduino to interface to the PC, which tells it where to go to effectively. You could probably do this with a Raspberry Pi, I expect, a Wi-Fi one, a little Zero. Then it may be able to be autonomous. You needn't connect anywhere. You could do all the calculations, all the updating of the orbital elements on the Pi. So that's.
Walks down add-on. On the list, 2 weeks, he said.
So. So this is the controller. The two chips, really. These are the DiSEqC chips. They're really switch mode LMB controllers. You either get 13 volts or 18 volts out of them, and you just select with an input pin. Normally for satellite service, 13 volts vertical for an LMB, 18 volts horizontal, and you just feed into a pin a 22 kilohertz waveform, and it modulates the 18 volts on the output. Fairly simple. It's all SOIC stuff. It's CAT1206 DiSEqC, so it's the largest size of surface mount. So it's it's not too difficult. The only difficult thing is the CAT22. You get to the bottom of the data sheet and they say, by the way, there's one of these little pads underneath the chips you have to solder. So that was the only tricky bit, but I'll pass this round. All I've done is left holes in the bottom with a plated through hole and just fill it with solder. It's really simple enough. There's a prize for spotting the one unsoldered component. But how do you connect these two? Wrong computer. How do you connect the two motors together? Well, there are other disadvantages that they don't move very fast, about 2 or 3 degrees per second. So when the ISS is going overhead, you'd be there all day trying to catch up with it. So the best way to do it is the same as the catapult DiSEqC Hilly, where they have two horizontal rotors at right angles. The lower rotor is aligned east-west and tilts the assembly north-south, and the upper rotor, in the static position where it is here, is aligned north-south and tilts east-west. So, as you can see from that, if the satellite goes over your head, it's no problem at all. You just look over your head.
3.8 metres. Yeah, I mean, I just got the question. That's a 3.8 metre dish that we use to track the ISS with at Goonhilly, where all the Tim Peake pictures came off this dish.
Mm-hmm. The equations for working out the angles are a bit more difficult. Normally it's just azimuth, elevation. But when you've got this, it's effectively the other way around. Effectively you're elevating first, then you're doing rotation, and that changes the azimuth and the elevation. So you end up with these equations, but they're not too bad in software. Once again. So means of connecting them together. This is my first thought. 2 L-shaped brackets bolted together in the middle and bolted onto the rotators at each end. I like not knowing much about mechanics, it seemed to be best when it was symmetrical. If you could do that rather than that's not symmetrical, of course, the more symmetrical you keep it, then you'll equalise the loads going one way or the other. So that's my first thought. Then there was this one. So looking down on it, you have 2 bars at right angles, and the dish will be here. So your dish will be rotating this way and that way. But it might clang that as it goes down that side. So possibly not. Then Rob suggested this one, which is the one we have now. Keep it simple. Just holes in opposite sides or adjacent sides of the block. Top rotor upside down. There's also possibility of counterbalancing it. Obviously you can't counterbalance the antenna, and it's end-mounted antennas only, because the other thing, your counterbalance has to move through the support, so you can't do that. So you can counterbalance on the shaft though. Put an arm there and put some weights on the bottom, so as it tilts into the screen, the bottom tilts out of the screen. So that's something I haven't experimented with yet. But I think you might be able to do the same on the top. It's a bit more difficult on the top because it's 2 things are moving really. So further research required. So there's effectively what we have there. 2 joined at right angles, and they both move roughly plus or minus 90 degrees. Not quite, there are some limitations. That's the full test setup. So I'll just set it going. Got the software set up on this laptop. There's the controller. I'll just do a manual movement so you can see.
You want that one on the screen, Brian?
Not for the moment, maybe when I'm doing a pass later on. But, I'll just do a manual command to send it somewhere. So So the lower one's going to minus 75 degrees, and the top one, you can catch it, Dave, it comes your way. Wrong way. The command for the top one is the other way around because it's effectively coupled backwards, so it's moving plenty fast enough. The ISS, you only need about 1 degree per second. It's not very much at all, even when it goes over the top of you. Once you have the rotator on top, it can just do that. There's none of having to do that with the standard type. I'll just send it back to the park position. The software that controls it in practice, there's several of these tracking programs, some of them free. Orbitron seemed the simplest one, and it was free. It's the software isn't actually updated anymore. It's quite old, but it goes away and it gets the orbital elements, the satellite predictions automatically, and it outputs azimuth and elevation, which is all you need really. That's the software that's running on here. This is taking the data from Orbitron. That comes straight in. It goes through those two equations that were on the bottom of the screen earlier, and it sends the commands out to the motors with the DiSEqC protocol. The ISS is inclined at 51.6 degrees, so it never gets further north than 51.6 degrees. So in a way that's quite good for us in the UK because it's mostly to the south and allows you to do a bit of tweaking on because there are some limits in the motion of the rotators. If it's mostly to the south of you, then you can ignore movement to the north quite a bit. But when it's at low angles, it can still come in north of your local equator, even almost as far north as Aberdeen, in the same way that when you beam stateside, you're beaming northwest to get southwest effectively. So it's not a complete solution, but they have various limits, these rotators, and they're a bit conflicting. With the go to angle command, it's plus or minus 80, which is really annoying. But you can drive them with the software command or manually with the buttons on the rotators past that, but it's a bit annoying that they stop at plus or minus 80 for the angle command, which is the one we want to use. So because we have this advantage of it always being to the south, or mostly to the south, the top one is tilted 10 degrees to the south and reset, so it thinks that's 0. So it will now go to 90 that way and 70 that way. You still lose out a bit on the horizons, but ISS at the horizon's a bit tricky anyway, so you're not losing too much. So what sort of load can you get on? That's still under review. So I went to the local advanced torque test facility and applied precision loads to the rotors to see what they'd take. And it's the ALSAT, the one I started with. That's the one I've had on my domestic satellite dish for a while. 1.4, and these TM2600 M3s a bit chunkier too. So in theory, a 4 kilogram dish and 50 centimeters away from the middle, but it doesn't quite work out that way because you've got the weight of the bottom rotator has to tilt the weight of the top rotator as well. But they are pretty chunky. I'll pass one round. They are quite heavy, about 3.5 kilograms each. So if we look at the advantages first, I'm hoping this is going to come in about 130 quid for 2 rotators, about 90 quid delivered, about 15 for the little controller. The joiner bar, I've been trying to get some quotes this last week, but I haven't been able to track people down, but I'm hoping not more than 25. So 130-ish is a figure I'm looking for. The go-to angle, that's the one that really makes them easy to use. You just say go to whatever degrees you want with this limit of plus or minus 80, which we can sort of get round. No mains, no feedback at all. Not always an advantage, but it means there's nothing for you to process. And it's a rotate over elevate like the Goonhilly dish. 2 rotors at right angles horizontally, so it can easily do overheads. Arduino Nano, very simple system. And DDE is a sort of broadcast system within the PC. Orbitron outputs it, and anybody who wants to pick it up just listens for its DDE broadcast. The SAT PC32 as well I had to go with, but couldn't get that working, but maybe because I've got the free version, so I'll have to look at that again. Disadvantages. Who knows whether it will break them. They weren't designed to work this way. They're designed to hold loads at an angle, but is this the same sort of thing? So that's really the unknown, that's the experimental bit. End-mounted antennas, because the other end of the antenna, if it was centrally mounted, has to go through the support. You can't counterbalance the antenna because of that, but it might be possible to counterbalance the rotor and use a bigger dish. Slow speed, but fast enough for the ISS. Low torque. Again, depends what sort of dish you want to use on it. Dave's had success with 60 centimetres, I think, on 60 cm on your system, Dave, I think you're using.
So how big do you think that's, I mean, that is the $64,000.
I know,
How big a
it's,
dish do you think that is?
I've really got to try it and see. It's really more experimentation and how the counterbalancing will work. Or if you might be able to counterbalance the moments, but is that putting too much of a lateral strain on the rotor? And it needs more testing, really. And you never know where it is. Yeah, you told it to go somewhere. Did it get there? Is it going there? Is it working at all? I've added some extra circuitry over what they have in the datasheet to detect current from the supply to each of the chips, so I can tell when it's moving at least. So at least if I tell it to go somewhere, I see it start, but it probably got there. But they are very, very reliable. They're used in domestic circumstances. They're not used as much as this. Maybe some of them don't move at all, I suppose, when you want to change satellites, which may not be very often.
When you exceed the torque, does it just desynchronize the motor, or does
It stops the...
Smoke.
smoke signals to say it's left track?
Yes. Because they're meant to be used with satellite receivers generally have a 500 milliamp limit, so they appear to limit internally to 500 milliamps. So it may be just a case of changing resistor, and who knows. But I think the one that's going around, I think it says 12 volts on that motor, and they're already running at 18 volts. I've run it at 24 volts, but it didn't really improve it because it was shutting down because of the current limit, I think. So more experimentation again. This is the most annoying one. If you tell it to go to 70 degrees, and it goes, you see it's moving, you tell it to go to 71 degrees, it stops and starts up again. So when you're trying to track something going, the ISS going overhead, even though you only need 1 degree per second, because it's starting and stopping, and depending on how much you're updating it, that is a bit of disadvantage. So I've used that with the circuitry that's gone in to detect the movement. if the software wants to update it and it's already moving, it doesn't bother. It waits till it finishes. That's not quite as good as it's not stopping at all, but at least it's better than stop, start, stop, start. You might get some improvement on that. I'll set it going on a pass while I'm talking, so you can just see the general movement. I'll better make it a southerly pass, or we'll be into the wall and the board.
Did you want to put that on the screen, Brian?
Okay, yeah, just for a moment, just to show what it's doing.
When you're ready. That might reach it.
Does it reach?
Two inputs.
Thanks. So I've set it up roughly sort of mid-south UK. I think that's probably about Birmingham-ish. So we're here. The satellite's going to come from there and disappear over our left shoulder, my left shoulder anyway. And it should be fairly high elevation, I think. So Orbitron has a simulation mode, which is very handy for doing all these tests. I'll turn it back a bit. It's started a bit too early. Back. Go back, ISS. Go back. Yes. Tim, reverse gear. So it's elevation. I'll start it at 2 degrees to. No, we'll let it go to 5. So. Now it's just about locked on. We look at the track. Unfortunately, I've got it running a 10-second simulation. I wonder it's going so fast. I thought it was quick.
They wouldn't.
Right. I'll park it again and do that again. And this is if you look at the radar track. So it's 15 degrees per ring. Horizon's on the outside. We're in the middle. So it's coming into our southwest at the moment. So it's hit 5 degrees where it starts to track. It's got a long way to go to get on the right bearing. So this is where the not stopping it if it's moving comes in. It only sends another command if it's 10 degrees, the position is changed by 10 degrees or 10 seconds has elapsed. So it gives it longer rather than every second it's updating and stopping it. So it's coming up to 10 degrees in the southwest. North, by the way, is looking more or less where you are. So it doesn't have to move very fast. We're updating the rotators every 1 degree. It's a very rough approximation. Bottom one and the top one along a right angled triangle, and take the hypotenuse, and if that's 1, then you update it. If you wanted to update it every single second, can I do that? No, I can't change at the moment. The program's too big for the screen. I can't press the save button on the right. I'll just hurry it along a bit so we see what it's like when it gets closer. Just to be awkward, I'll try and make it a near overhead pass now so you can see what happens as it goes over the top. It's catching up, of course, because normally the ISS wouldn't be doing this sort of thing. Houston, we have a problem. So it's still only at 40 degrees elevation. And it's moving about, what, half a degree elevation. Well, looking at the rotors, the lower rotor's going about 0.4, the upper rotor's going about 0.5, so fairly gentle movement. Hurry it on a bit more. Stop it. The location's a bit more south than UK, I think, because it's it's probably northern France type of latitude. Let's look at the elevation now, nearly, or just past peak, and it's only going by 1 degree on the upper rotor, so well within capabilities. We look at the radar again, so it's now to the northeast of us. Let's move it on a bit more. You'll probably find as it gets low down now, because we've counted it 10 degrees to the south to help us, it's probably going to run out of movement to the north. Not doing so bad though.
It's all right. No, it's all right. It's all right. Clear.
There is a stop button, as you can see, for precisely this sort of thing. Not sure what's going to happen when it gets to the end and parks itself. It may go that way first into the board. We'll have to see. So it's going to stop at 5 degrees, so we can hurry it on a bit more. So the lower rotator has now run out of range. It can only go to plus 70 north. So it means it'll be out of position for the rest of the pass, but only very slightly.
You're not going to see that anywhere.
So it's about to park itself. So it's stop tracking at 5. You can give it a rest if you want, then park it at 0, 0. Is that going to miss?
Yeah, I can manage it anyway.
Then you have the option of pausing it, so it's you have to start the next pass manually. Sorry, I think my voice has gone. Testing. So that's about it for the demo. We can go back to the other system, just do a bit on DiSEq.
To keep himself in a knot. Hang on.
So DiSEq invented by Eutelsat, sending signals down the cable to LMBs, rotors, etc. with 22 kilohertz tones. We're on 1.3, which has this DiSEqC, which is very handy. And you may see this on satellite receivers. It uses the DiSEqC. If you set it up, your dish, you align it to the geostationary arc, and as long as the satellite receiver knows your latitude, it knows exactly what angle to tell the rotator to go to get to the satellite you want. This is what the data looks like. So you have 0 and 1 bursts, 650 millivolts peak to peak, and you send bytes. So they're the only two commands you need, really. Stop and a few others, but they're the main ones. So very simple. The controller, there's a 22 kilohertz tone comes in, that gets fed to the modulation inputs of the two little controller chips. Which are these. Select 13 or 18 volts, so that's where your 22 kilohertz goes in. I've added some circuitry to do the detection of current coming in, so I know when it's moving. But it's pretty simple, really. As for setting up, as long as you make sure everything is square, the bar is vertical in both planes, you need to get to local south, and then you need to align the dish if it's an offset one. When I was looking for what time local south was, so I could put a rope on the pole and walk around till the shadow went down the pole, I was surprised to find that local noon isn't the same every day. It can vary plus or minus 15 degrees throughout the year because of the way the Earth is moving around the sun. So you could be several degrees out unless you look this up. and find out exactly when the sun is south of you. You see today it's not bad, it's only 3 minutes out, but 2nd of November, that's probably its maximum. This is at Greenwich, so it should be, you'd expect it to be 12 every day, but apparently not. We don't actually need solid dishes for 2.4 gigs, so some experimentation to be done with these wire mesh types. Found this one on the internet. Doesn't look like it weighs very much. So it's 2 meters. A 1.2 version of this would be very light, I would think. So further experimentation required. That's just closed in, just bent plastic tubes effectively, and chicken wire. So something else I want to have a go at. That's about it. So it's still sort of in development. If anyone wants to have a go, it'll be an alpha tester. There are 3 of these bars going for a small donation to BATC funds, and I've got several of the DiSEqC PCBs for similar. So if anyone would like to have a go, see me after. Hopefully, when I worked out exactly what size dish you can get on it, and it's going to be reasonably a reasonably safe bet, then I'll make it into a proper project. But that's about it.
Any questions?
Presumably you can use it to track any object. You can use it to track any object and any amateur satellite, and it would be strong enough to carry something like an arrow antenna.
I think so, yeah. As long as Orbitron or whatever can get the orbital prediction for it, then it can track it. It can even track geostationaries. So that's one way of lining it up. I've been using that. Set it up, make it go to Astra, then make it go to somewhere else, and just tweak the dish. And if it's going to both of them, it's a fair bet it's aligned well. So you could put it to SS Hailsat as well.
I'm just wondering about the maintaining the polarisation of the antenna. Would you normally configure it for circular to deal with that issue?
That's right, yes. ISS, the ham TV is circular.
Okay, thank you.
I see what you mean, because it's got all over the place for a linear, so it has to be circular.
Can I just ask where the motor is and the control board? We haven't seen anything down this end.
Behind
It's on its way around. Your seat about when?
Any other questions?
Have you tried to evaluate what the net pointing error is roughly?
It's probably down to the way you set it up as one source of error. The angle you can tell it to go to is in 1/16 of a degree. Whether it's actually that accurate, I'm not sure. When I got them, there wasn't any play in them. I'm not sure if it's the way I'm using them, but there's not very much play now. There isn't the bottom one. Maybe that was the torque test one, I overdid it. But the top one is hardly any play in that at all. So, with the, I think with a 1.2 metre on 2.4 gigs, the beam width is 6 degrees, is it? It's quite a lot.
So if it's good for satellite, KU band satellite pointing as a single positioner, taking 2 into account, approximately 1.5 times, say,
Yeah,
it should be pretty reasonable on 2.4.
should be.
Yeah.
So,
Okay.
remains to be seen, but it should be.
Jolly good. Right.
I presume it's a pick or something in the controller.
Oh, do we know? Oh, in there, it's a Holtec HT48, which I haven't heard of before. So
I'm wondering if you're thinking.
do the software, yeah.
Yeah.
The ALSAT, you can take the chip out, but I think that's soldered in that one. But that's another project, yeah.
It's only single-sided.
Mm.
So far.
Sorry?
How long has it actually been up in the air so far?
It's still only in test mode. It's been in
Right.
inside the house mostly. I haven't actually received the ISS with it yet. I've only had, when I was ready for 2 passes of the Yota last month, and I had some problems with it, and since then I haven't been sure whether it's been on or not. And my garden is so terrible that I have to go portable to test it. But this last week a tree has been taken down, so I've got a lot more now of the high passes to have a look at, so I'll be out there next week.
For information, I obtained a similar rotator on a 900mm dish, which was for tracking Clark belt. So one imagines this will should stand up to weather pretty well as a commercial design. So I think with perhaps a little counterweighting, you may go to quite a sized dish on it. This was a solid dish.
Do they spec? I mean, is the TM spec on a dish size?
I think it's 1.2 and it's a normal configuration on that arm. But then again, it's not, the moment isn't very great. It's not very far from the axis of rotation.
Yeah.
Whereas it's for the bottom rotor here, it's a long way out. I've hung a 3 kilogram weight on the end of the little dish, and it slowed down, but it kept going. So it's it must have been less than 500. It would have shut down, because when I put 2 of those on, it did shut down.
Okay, well, thank you very much for that presentation, Brian. We've been thanking Brian in the normal.
Thank you.